Hello, this video is for physics for Monday, August 24th. Today, we're going to talk about how science works. That's just my way of saying, what is the scientific method? So every time a scientist approaches their work, there's a certain process we want to follow. And it's a very specific, a very orderly process. Now, there is some repetition or some cycling through, and I'll explain that with the black arrows below. But it's a very thorough process, and it helps us make sure that we don't make any mistakes and we're following a logical process to come to a logical conclusion. The first step in this method is that a scientist looks at the world around them. You observe things, you see things, and it makes you wonder, why does that work? How does that work? That's the first step. Something grabs your curiosity. The second step in the process is to, well, let's pay a little bit more attention to that. Let's observe it a little bit more closely. Not simply we've gone from an interest to now what's going to observe. What can we see? What can we observe about this thing? It could be something as simple as, why does the rock have this mineral structure? It could be, how do volcanoes work? It could be, how does an atom form? How does the nucleus react? How does the universe move? How do solar systems grow and develop? So many different things. Just look around you, see something that interests you and you're curious about, and observe a little bit closer. See what you can see, what you can learn about it. The third step is to come up with a possible explanation about that observation. So let's just say you look up at the sun and you see that when you look up towards the sun, you can feel the heat coming from it. Well, why might we be feeling heat from the sun? And you come up with an idea, which is, say, because it's light, so it's glowing. We're used to glowing things being hot. And we would then come up with that's our explanation. We think that the sun is, the light from the sun is hot. The sunlight feels hot when it hits our body because the sun itself is hot. And we'll call this a hypothesis. This is our idea. This is our hunch that this is what's going to happen. The sunlight is warm because the sun is hot. Right? So it usually has that kind of structure. The next part of our process then is, okay, now that we have a hypothesis, how can we design an experiment? What can we do to perform an experiment to test our explanation? Right? So we could do a couple different things. We could set up something to measure the temperature when the sunlight hits something. Right? Just put a thermometer on a black piece of paper, for example, and does it get hot when the sunlight shines on it? Maybe that's an idea. But we do something to test our hypothesis, test our explanation. And then two things are going to happen, right? Either that test is going to confirm, right? The experiment confirms your explanation, or that experiment is going to contradict. It's going to show that it's false. So maybe we put the thermometer on that black piece of paper, we shine the sunlight on it, and it gets colder. Well, then maybe that doesn't make sense. We've got to go back and we have to think a little bit more about what our hypothesis is. All right. So eventually we're going to come up with a hypothesis that we designed some experiments, and those experiments are confirming our explanation. So the next step is, after you've confirmed your theory, after you've confirmed your hypothesis, we're not to a theory yet. After you've confirmed your hypothesis, then maybe then a scientist would publish a paper or share what they have learned with colleagues. The next step is really, really crucial, and that's others perform experiments to test your explanation. Right? Maybe your test wasn't very good, or you had a flaw, or something else went wrong during your test. You want your observation to be repeatable, right? So if somebody else wants to test your hypothesis, they need to be able to repeat the experiment you did, do something else to confirm what you did. Right? And then comes the next step. Do other experiments contradict your experiment? Well, then there's still not something quite right with our hypothesis. We got to go back to the beginning and come up with a different explanation. But if our other experiments do confirm our hypothesis, right, then we go on to the next step. In our explanation, now that it's been supported not only by our experiments, but it's been supported by others' experiments, we can now call our hypothesis, our explanation of what's going on, we can call this a theory, right? It's been proven true multiple times, right? It's not just simply a one-off thing. Multiple experiments have been done. They all are supporting your hypothesis. and that becomes a theory at that point. And then our final step, once you have a theory, now we come up with the real world. Now we got to come up with applications. What can we do to use that theory? Right? Now, I did my research on electrons, and I was looking at the nucleus. I was actually running those electrons into protons and neutrons, and I was trying to hit the quarks inside of them. So we did our theory. Our experiment was very good. It helped support some theories. But you want to talk about coming up with applications? Not so much. Sometimes research is done very basic. But sometimes theory has more immediate applications. Think of solar panels. When I was your age, hardly anybody had any solar panels. They didn't work very well. Well, some people started working on it, doing experiments. They developed their theory, and they figured out a way to build a better solar panel. And there's a good application of how the sunlight interacts with that material to produce electricity. So the end goal, you really want to come up with, what can you do with that theory? The knowledge is great. Your theory is great. It's the application where it really meets the real world. All right, so that's our scientific process. Just to kind of go over it once more, we observe something, we're curious about it. We observe it a little bit more closely, see if we can learn a little bit more, and we try to come up with an idea then. What's causing the thing that we're seeing? What causes that? And then we can find some experiments, right? We want to make sure, we want to test our idea. Does our idea work? Does it really explain what's going on? If it does, then we move on to the next step of our process, and others are going to do our experiment as well, or change our experiment a little bit, but they're going to try to prove our hypothesis true as well. Okay. Once our hypothesis is proved true by multiple experiments, then we can call our hypothesis now a theory. And the next step, come up with applications. So I want to share this last piece with you. Humans were born as scientists, right? We're curious, especially when we're young and we're learning, and the world around us is very new and we don't understand it. We experiment a lot. And so I like this picture here, the little baby playing with the bubbles. Oh, wow, they're really cool. These things are floating. They're fascinating to a young child. Well, you grow up a little bit, and bubbles are boring. You've seen them. You know how they're going to pop when you touch them, and they're going to float up and down and move around with the wind. But so they're not as interesting to you as they once were. So the thing is now, how do you find things that are interesting to you? Something you maybe haven't seen before, right? We can always learn. There's always so much in this beautiful, complicated world that we live in. Something that would catch our eye that we can ask some questions about and try to come up with a theory of how the world around us works. I want to close today's notes with two questions. And the first one is, how many experiments does it take to disprove a theory? What do you think? How many experiments does it take to disprove a theory? Well, hopefully you came up with the answer of 1, right? If a single experiment shows that your theory is not true, then you must have a problem. Your theory is not accurate, right? It's been disproven. Now, it may mean you need to tweak your theory a little bit or expand your theory a little bit, but the theory as you stated it is not true as soon as just a single experiment shows that it's not true. So let's ask the other side of that question. How many experiments does it take to prove a theory? To prove a theory. Think about that one for a moment. Hopefully you come up with the answer that something along the lines of this. There is no number of experiments that are enough, right? We can have one experiment support your theory, 2 experiments support your theory, 3, 4, 5, 6, 7, 8, 9, 10, 100, 1,000 experiments support your theory. But that doesn't necessarily mean it's true. It just means we haven't found a time when it's not true. I'll give you one quick example as I close out the day. When we talk about mechanics, and we'll do that a lot later in this year, and the idea of Newton and how we have F equals ma and how things move and go through that. That worked well for many, many years, hundreds of years. That explained a lot of the phenomena around us. But as we got into the turn of the century or in the early 1900s, we found out that wasn't quite true. And people like Einstein started making predictions. That's not entirely accurate. And we could come up with some experiments that proved that the old Newtonian ideas of mechanics were not true. But they worked really, really well for the world that we usually see. Right? So as soon as we come up with one, that disproves it, it means our theory is wrong. Now, it doesn't mean the theory is not useful. It just means it's limited in what it can be applied to. All right, guys, thanks for listening to this video. Take care, and we'll talk to you tomorrow.